Hi, welcome to the presentation on simple N-nary tree design. So before we go ahead, let's look at what's an N-nary tree. As I understand, N-nary tree is a tree where every node can have a maximum of n children. So this tree design, the purpose of this is to more illustrate how you can you implement a tree in C++, but before jumping into the implementation, I thought of introducing the design with the data structure. And this particular design, though it's in use, we will see what are the issues and time complexity and things like that. But this is just to show an implementation in C++. So let's directly go into the design. Every node in this tree design has these fields. So every node looks like this. It has a name, it has a node ID, it has a parent ID, and it has a data. That's some user-defined data, and it has a list of children IDs. This is an important point to note that this is not having a pointer or address of its children nodes. It is just having a list of their IDs. For root, we just reserved the root ID, and parent ID is again reserved as the max of 4 bytes. The 4 bytes is just assumed for this design. It's not restrictive and we can actually generalize. So the tree would be nothing but just a list of such nodes. Okay. Let's look at a couple of examples. A simple example with just one level with the root at level 0 and then it's 3 children. So this is a tertiary tree. Sorry. So we have root with ID 0 and then child A, B, and C with IDs 1, 2, and 3. So how they are represented, you have the first node as the root with ID 0, and then next you have in the list the child A, then child B, and then child C. Root has the list of its children IDs, so 1, 2, and 3, and each of these other child nodes, ID 1 has parent as root, which is 0, and then same thing goes to the node B and C. Second example, we have one more level here. So we have second level, and then we have root with child A, which has further children A1 and A2 with ID 4 and 5. Root has a child B, which has no children. And then root has child C, which has just one child, C1. So how is that represented? Again, root remains the same with the children list 1, 2, and 3, which are respectively A, B, and C. And A has a change, wherein the children ID list is not empty now, it is 4 and 5. And then B, it's the same. C has just one child list, which is one child in the list, which is 6. And then the children A1, A2, and C1 are just added. So the list is now consisting of 1, 2, 3, 4, 5, 6, 7 nodes. So list of 7 nodes is this tree. What are the operations that we can do on this on a tree in general? And we can look at how we do that. So adding a new node B to parent, it is nothing but simply appending that node to the list and giving it the new ID, say N, and then updating its parent ID. So the parent ID of A would be the ID which would be here in node B. And then we would take N, which is the node ID of B, and add it to the A's list of children ID. So pretty simple operation. Removing a node B with say an ID M Now, this would be a little bit involved in the sense that we'll have to find the node with the matching IDN, which is straightforward. Then we find the children of B first and remove them. So intuitively, you may think that this would be a recursive call because the children would have further children. So we keep going ahead till the entire subtree of B is removed. And finally, we remove the node B from the list. And finally, find the parent node of B and then remove B's node ID, say N, from the list of children ID of the parent. Operating on a subtree of the node, it is one example we already given is like removing a node. So essentially, you would find for each ID in the list of A, node A, suppose you want to operate on a subtree, you are basically finding the low node in the list and then operating on its subtree. And this is going to be like a recursive call. So I'm just like generalizing a little bit of what we talked about for remove. Time complexity. We will look at a different time complexity for adding a node, removing a node. Removing a node, do we really think that it is just order of n? The way for adding a node, it's just appending a node to the list and it would be order of n. So would removing a node be just that? So it would be good if you just give it some time and think about this. While I'll in the next subsequent video, I would discuss the time complexity and probably also discuss the implementation as well. That's all for now. Thank you. Bye.